when it reaches to the satellite. That's why in satellite communication we are using the circularly polarized antenna so that it can receive the signal with any polarization, with any type of polarization. Okay, so this is the advantage of circular polarization. Wide research is going on this field, circularly polarized antennas. Either it is a microstrip antenna or a DRA or any other type of antenna. There are so many types of antennas there. Another thing is wideband or ultra wideband DRA. It is also a very famous area to designing a wideband where we have a very large, you can say that bandwidth. It supports. Let us suppose that if I am talking about the UWB ultra wideband, so FCC recommends that the ultra wideband is from 3.1 to 10.7 gigahertz, such a larger bandwidth up to 7 gigahertz. Okay, so there are different techniques available in literature to design such type of antenna, wideband or ultra wideband. And fourth and very important one, which is widely used in 5G communication system, is a MIMO antenna. MIMO antennas, where we have a multiple antenna on transmitter side, multiple antennas on the receiver side. Okay, so it will I will discuss later on what is that, what is its advantage. Okay, now come to the serial device, that how can we generate the multiband characteristics in DRA. So multiband characteristics, there are so many techniques available in literature. I summarize this thing in 3 points. One is by using the multiple DRAs. Multiple DRA means, let us suppose that if I am using the 3 DRAs of different size, then each DRA is radiating in a different frequency band. Okay, but the problem with this technique is that your overall physical size will increase. The antenna physical size increases, or it is actually not a very efficient technique to generate the multiband characteristics. Another one is a hybrid DRA, where we have a combination of 2 different resonators. One is a dielectric resonator, another one is a patch antenna. Let us suppose that patch antenna. Patch is radiating in some other frequency, DRA is radiating on some other frequency, and you can generate a multiband characteristic. Simple. Another thing is that you can also create a multiple radiating modes inside the DRA to create a multiband characteristics. It is very important technique, and it is not very easy to generate the multiple modes inside a single ceramic material. Okay, but it is an efficient technique because each mode, let us suppose that I have 2 different modes. One is TM01, another one is TM02, each having a different resonant frequency, because each mode having its own cutoff frequency. So each having the different frequency, and multiple radiating or multiple resonating peaks are created. Okay. Now I have given one example of my paper. How can we generate a multiband characteristic? It is a hybrid antenna technique, where we are using patch, this monopole, and this monopole or metallic strip is used to excite the ceramic material. Okay, and when you excite this ceramic material, then I have 4 different peaks, 4 different resonant peaks. Okay, one is on this point, 2.5, another one is at 3.2 and 5.0 or 6.0. Okay, and if you see this resonant, when we analyze this structure, this resonant peak is due to this monopole, and remaining 3 resonant peaks are due to the ceramic. Okay, now I perform the modal analysis of this structure, that it is actually used to find out which type of mode is created inside the DRA. Okay, so let us suppose that मुझे क्लियर नहीं है कि आपको समझ में आएगा कि नहीं, बिकॉज आई थिंक ऑल ऑफ यू आर अवेयर विद दिस TE and TM modes. TE and TM modes, it is clear to all of you. In case of a TE mode, what type of field is generated? In which direction? If I am talking about the electric field, let us suppose that if I am talking about the electric field, then in case of a TE mode, which electric field is created? How the electric field is created? If I am talking about the z direction, let us suppose that this is my z direction. There is no change in the electric field. Electric field is constant. This is called as a TE mode. Okay? There is no variation in electric field along the z direction. Similarly, if I am talking about the TM mode, so there is no change in the magnetic field in this direction. Magnetic field is constant. While in case of a hybrid mode, if I am talking about the hybrid mode, then in the direction of wave propagation, that is the direction of z, it is the electric field and magnetic field is not constant because of the hybrid mode. Okay, there is a variation of electric field along the z direction. There is a variation of the magnetic field along the z direction. However, which one is dominating? It depends upon HE or EH. ठीक है, in case of HE, EZ is dominating. ठीक है, while in case of a EH mode, HZ is dominating. Okay, so if you see, this is the z direction. This is the direction of propagation. There is a variation of electric field. This is the electric field distribution. This is the E field distribution on a ceramic material. So if you see, there is a variation. There is a variation of the electric field. While in this case, if you see carefully, there is a minute, very you can say that very small deviation in electric field. Here the deviation is large, here the deviation is small. So that's why it is called as HEM11 delta mode, where EZ component is more dominating, while this mode is called as HEM12 delta, or it is also called as EH11 delta. EH11 delta means EZ component is suppressing, while HZ component is more dominating. Okay, that's why the electric field is minutely deviated here. That's why it is called as HEM12 delta. And the third mode is HEM21 delta. Okay, here also the variation is there. Okay, now how can you create this 2-1 delta? This shows that in which direction how many half-wave variations are occur. So this is R, phi and Z. Okay, so along R direction we have two variations. Phi, that azimuthal direction we have a one variation, and delta is along the Z direction. Okay. Now one more thing which I want to discuss here is in case of a DRA, as I already discussed from the first slide, that dielectric resonators are widely used for storing the EMFs initially. Okay, so in case of a DRA, there are lots of mode which is not used for radiating purpose. Okay, you have to identify that which mode is for radiating purpose, which mode is not for radiating purpose. Okay, so this mode is non-radiating mode. Or in any of the structure, if non-radiating modes are created, then it will also affect the characteristics of the radiating modes. Okay, so you have to suppress such type of modes. So we have used some technique to suppress this mode in this structure. This thing. This is the under structure where we create the multiple modes to create the multi-band characteristics. Okay. Now come to the circular polarization. I already discussed this thing, that Circular polarization I have already discussed. This thing. What is that polarization and how it created, what are the classification, vertical, horizontal, RSCP, LSCP, how we see. So we are using the term axial ratio, okay, to find out this structure is circularly polarized or not. Okay, let us suppose that if the major and minor axis, that is Ex and Ey, is equal, then only you will get an axial ratio which is equals to 1 or a 0 dB, then only the structure is called as a circularly polarized. If this condition is satisfied within your operating band, okay, this condition, that means major axis equals to minor axis, then only this elliptical shape becomes a circular shape. I think it is clear to all of you that if the major axis is equals to minor axis, then that structure is called as circular. Okay. I already discussed this thing. What is the need of circular polarization? Now come to the part. How can we generate the circular polarization in any of the radiating structure? So in case of DRA, I have given one example of this structure. That it is a very basic structure. Here the authors have used the two. I think it is clear, it is visible to all of you that there is a vertical strips here, okay, and these vertical strip is connected with this line, okay. Now this line creates a orthogonal modes, okay. It is a lambda by 4, so it will create orthogonal modes, that is Ex, one mode which is along Ex direction, another mode is along Ey direction. Now another thing is that the second condition, there are two conditions in circular polarization. One condition is Ex is equals to Ey, and second condition is there is a phase shift of 90 degree between Ex and Ey. Okay, so how we generate a 90 degree phase shift? In 12th class there is a formula that phase difference is equals to 2 pi by lambda into path difference. I think it is clear to all of you that phase difference is equals to 2 pi by lambda into path difference. Now, if you create a path difference between two field lines, then you will create a phase difference of 90 degree. But path difference, if path difference is lambda by 4, let us suppose that path difference is lambda by 4, then phase difference will be 90 degree. Okay. So, if this conformal strip having a shorter length, this conformal strip having a larger length, this will create a path difference between two field lines. Okay, and that path difference, we will optimize this path difference, and after optimization, we will get a phase difference of 90 degree. Okay, so both the conditions are now fulfilled. First condition is Ex is equals to Ey, two field component which is equal in length, equal in amplitude. Another is Ex and Ey having a 90 degree phase difference. Okay, so that's why this structure is operating between 2.92 to 3.17 gigahertz, and axial ratio we will get at 3.3 to 3.62. That means in between this operating band, the axial ratio will goes 3 dB, lesser than 3 dB for this frequency, and that's why this structure is called as circularly polarized antenna. Okay. Similar type of case occurs in this where here we are using the two conformal strip of different length. Here we are using the two DRAs, two ceramic material of different length, and shifted so that we got a two different field lines. Okay. Now come to the another topic, and that is how can we generate a wideband or ultra wideband characteristic. So there are so many things. One is that if you are creating the multiple frequency band and it will come closer in a frequency, so now the structure becomes wideband. Another thing is that if you reduce the quality factor of the antenna, if the quality factor reduces, then the bandwidth is increases, because bandwidth is inversely proportional to the quality factor. Okay, so in literature there are so many techniques are available, like we are creating this air gap. If you creating the air gap in any of the ceramic structure, then what happens? If the air gap is created inside the ceramic material, then overall effective permittivity of the structure goes down. Okay, if the air cavity is created, if the air cavity is created, the effective permittivity reduces, and as the effective permittivity reduces, the quality factor goes down and bandwidth becomes more. So this type of techniques, the splitting of DRA, is also creating the air gap. Some air gap between DRA and the metal and like surface is also used to reduce the quality factor. Okay, I have given one example of my published paper, that here we are using the different techniques to create a. I will not discuss in detail why we are using the different techniques. Like firstly, we reduce the quality factor of the structure. Okay, for reducing the quality factor, we are creating an air cavity. This is a cylindrical structure. Then I create a cavity, air cavity, and then after that I put a Teflon. This material is aluminum, whose permittivity is 9.8. Okay. And in between we have a Teflon whose permittivity is 2.1, and if you combine these two structures, one is a alumina whose 9.8 whose permittivity and Teflon 2.1, so the effective permittivity of the structure goes down. Okay, and if you see the structure, then I again use the alumina over this. So when you do all these things, then I got a bandwidth of from 3.1 to 10.7 gigahertz. Okay, 3.1 to 10.7 gigahertz, which fulfills the requirement of FCC. Okay, every country having its own ultra wideband frequency range. And in India, we have a different frequency range for ultra wideband. This is for US. FCC is designed by US. Okay, and he actually they fixed the band from 3.1 to 10.6. It is widely used for indoor application. So this is how you can create ultra wideband. Now come to the important, which is in line with this FDP, that is 5G and 6G. Now I come to that part, and we start this thing with the multi-input, multi-output. Okay. In case of we have a different research area. I have classified this research area into 5 different parts. Okay. Starting with the what is MIMO? And how can you design, what are the challenges when you design a MIMO antenna from single port to multi-port. Okay, then we will move towards the millimeter wave, okay, which is a very important band for 5G. Then we will move towards another, you can say that another characteristic which is known as quasi-isotropic antenna. We will discuss what is that. Antenna design for cognitive radio, more smarter system. Cognitive radio, I think all of you are aware with the cognitive radio. How can you design antenna design for cognitive radio? We will discuss. And beam splitting or beam tilting phenomenon. It is also very important for 5G communications. So now, initially we are talking about the single port antenna, which is used for CISO systems, single input, single output. Now we will move towards the multi-input, multi-output, that is multiple antenna on transmitter side, multiple antennas on the receiver side. Okay. We have two different types of format for MIMO. One is a spatial diversity, another one is a spatial multiplexing. Okay, in case of a spatial diversity, I have put one diagram here. You are transmitting the same message signal by using multiple antennas. My message information is that 101001. Okay, and I transmit this information to multiple antennas. Okay, that will increase the reliability. Okay, another one is spatial multiplexing, where we divide the original message stream into a different small section and transmit this message stream through one antenna, another message stream through the second antenna, and this will go and on and on. Okay, this will increase the capacity of the system. So we are using the two different formats. One is the spatial diversity, another one is spatial multiplexing. Okay. So by doing so, what we are trying to do, we are trying to enhance the data. Okay. According to the Shannon's formula, we have a V log to 1 plus SNR. So either the capacity is increasing if either by increasing the bandwidth or by increasing the SNR. Bandwidth having a limited bandwidth because the spectrum is very costly, so you cannot use biggest spectrum. It is a very costly. Okay, the purchasing of a spectrum is too costly. Okay, so bandwidth is limited. Now there is only one part which is called as SNR. So either if you want to increase your SNR, either you have to increase the signal power or you have to reduce the noise. Signal power again having a limitation from the telecom agency, you cannot go beyond that signal power. Okay, so it is also restricted. Now only part is you have to reduce the noise, and noise reduction can be done through a MIMO system. Okay, we have transmitted multiple message informations or similar data through a multiple antenna, so it will reduce through a fed-in channel, so it will reduce your error probability. Okay, so this is the advantage of MIMO. Come to the how can you generate or what are the present in such areas. So I have already discussed this thing, multi-band, how can you generate multi-band, wideband. The main thing is the isolation. In case of a MIMO, if you are designing a MIMO antenna, you have to take care about the isolation. Isolation means, let us suppose that I have a one port and I attach another port just adjacent to that. Then there is a coupling between these two ports. First port coupled with the second one is coupled with the one. Okay, and it will actually change the characteristic of the individual antenna. Okay, that coupling. Okay, so you have to reduce that coupling. So that is called as isolation enhancement, and we have different techniques to reduce the isolation. Let's suppose that we have a orthogonal. I think all of you are aware with the polarization diversity techniques. Okay, polarization space or pattern diversity. So if let us suppose that one of the important area is polarization diversity, modification in ground frame, uses of FSSS and VG structure. Okay. Now this is also my published paper, and here we are using the modification in a ground plane. Okay, ground plane modification have done to improve the isolation. So if you see carefully here, I have put the three surface current distributions here. One port is excited, another port is terminated with match load. Okay, then one port is excited. Initially, when I use any type of modifications in a ground plane, then the surface current is distributed over entire ground plane. Okay. Now after that, in the second step, I have put two metallic strips on a ground plane. Then some of this current distribution is reducing and it is moving towards this side, which is excited. After that, I have put a slitted ground plane, and when I use the slitted ground plane, then the current is entirely moving towards the excited pole. Nothing go beyond this. Okay. So if you see its isolation on mutual coupling, that is S12. S11 is a reflection coefficient, S12 is a mutual coupling. Okay. So if you see the mutual coupling between pole 1 and pole 2, initially when conventional ground plane are used, then it is approximately minus 10 dB. When I put this metallic strip on a ground plane, then it is reducing, and after that again it is reducing when I use the slitted ground. Okay, so this is one of the technique to improve the isolation between the two poles. Okay, but it is used only for you can say that for S parameter based isolation. There are two types of isolation in MIMO antenna case or in an antenna case. One is S parameter based isolation, another one is a far field parameter based isolation. So here in this structure I am talking only about the S parameter based isolation. It is an answer. While far field is also important. Far field isolation is also important. How can we do that? We will discuss. This is one of the structure to create a circular polarization. Okay. Here I contributed this is the structure where I use circular aperture. In case of a circular aperture, there are two field components. One is Ex, another one is Ey. Both are equal. So again, when I contributed this structure, then some part delay is created and phase difference is created. So we got some axial ratio. Now the main point in this structure is that if you see carefully, one aperture is tilted in this side, another one aperture is tilted in this side. Okay, if you do this thing, then the polarization is changing. That means if it supports the LSCP waves, then this pole supports the RSCP. Okay, that means we are introducing the polarization diversity concept. Okay, one is creating the left-handed circular polarization, another one is creating the right-handed circular polarization. A polarization diversity is created, and due to this polarization diversity, again the coupling is reduced. Now come to that part that isolation can be reduced by two things. One is S parameter, another one is RC parameter. We have discussed the S parameter mutual coupling reduction or isolation enhancement using S parameter. Now come to that part, the far field parameter. How can we reduce the coupling of different antennas in far field? Okay, how can you do that? I have designed my antenna. This is antenna design, and if you see the far field of this antenna, this pole, it is broadside. That means if antenna is this is your radiator, and it is radiated in this direction. I have designed in this way: DR1, DR2, DR3, DR4. So DR1 is radiated towards in which direction? DR1 is radiated along plus Z direction. Okay. Similarly, DR2 is radiating along minus Z direction. DR3 is radiating along plus Y direction, and DR4 is radiated towards minus Y direction. So each port is radiating in a different direction. Okay. So the far field is isolated. Okay, for different ports. If you see the radiation pattern, far field pattern, so DR1 is radiated. The red part is the maximum. It shows the maximum radiation. So maximum radiation is along plus Z. DR2 is along minus Z. DR3 is along plus Y. DR4 is along minus Y. Okay. So each port is radiating in different directions. This is called as a isolation enhancement using far field. Okay, so there are two different types of right now most of the research paper are published on this field, isolation enhancement using far field. It is also very important. It will increase the coverage area of your antenna. Okay. Now this is the another technique. How can we reduce how can we enhance the isolation using far field? So here we are using the frequency selective surface over the antenna, and the frequency selective surface creates a phase gradient, and as the phase gradient is created, the radiation pattern is tilted. Initially this is along plus z direction, VR2 is also along plus z direction when we are not using the FSSS structure. When I put the FSSS structure, then VR2 is radiating in this direction, VR1 is radiating on this direction, and we will create isolation, okay, between two antennas with the help of this is the another technique. In this structure, I mechanically designed the antenna in such a way that each port is radiating in different direction. Why? In this case, we are putting both the antennas are radiated along plus z direction, but we are using the frequency selective surface to so that the radiator radiates in a different direction. Okay. Now come to very important part of 5G communication system, and that is known as actually I want to discuss cognitive radio. Okay, antenna design for cognitive radio. Before cognitive radio discussion, I have to discuss this reconfigurable antennas. Okay, so reconfigurable means your antenna having the capability that it can change that its characteristic, frequency characteristic or pattern characteristic or polarization characteristic or the combination of frequency polarization, frequency pattern. Okay, dynamically we can change. Okay, so we have it is widely used in efficient spectrum utilization. That is a part of cognitive radio. Avoid spectrum condition is also used for reconfigurable antennas. So we have a different types of reconfigurability. Like we have frequency reconfigurable, pattern reconfigurable, polarization, hybrid having other then frequency pattern, frequency polarization, or a combination of all the three. How can we generate the reconfigurability? So the reconfigurability can be generated through pin diodes, variegated diodes. Okay. In optical vision we are using the photoconductive materials, or physically we can also visualize using the structural iteration. Ferrite materials are also used to change its characteristics dynamically. Now I will discuss the frequency reconfigurable antenna, where we are using the pin diode or variegated diode to change its characteristics. Like how? I have given one example. This is a simple, you can say the dipole antenna, printed dipole. Okay. Here I use, because this is the optical antenna. So here we are using, or authors are using the optical switches, where both the switches are closed. When both the switches are closed, the frequency is 2.16 GHz. That means both are on. On, that means the size of the antenna is now this one. This is the size of the antenna. And if this is the size of antenna, it is resonating at 2.16 GHz. Okay. Now when both the switches are off, then now the antenna side becomes this one, and now the frequency is shifted to the higher side, that is 3.15 GHz. So now with the help of diode on and off, you can create the two different bands. One is at 2.16, 3.1. This is the simplest example of frequency. Now you can also generate frequency reconfigurability through the vector diode. Okay. If I am putting in this structure, the authors have used the vector diode, and I think all of you know these things. In case of a vector diode, it is a reverse bias diode. So as I change the reverse bias voltage of a vector diode, then its capacitance is changing. If you are changing the reverse bias voltage, then its capacitance is changing. As the capacitance is changing, the resonance peaks are moving on a higher or lower side. Okay. I think all of you are aware with the resonant frequency. What is that resonant frequency? Resonant frequency is simply, you can say that XL is equals to XC. Okay. Reactive, inductive reactance or capacitive reactance is equal. Okay. That means the electric energy at the resonant frequency, the electrical energy is converted into magnetic energy, magnetic energy is converted into the electrical energy. Okay. So now the thing is that as you change the reverse bias voltage, of a vector diode, then its capacitance is changing. As the capacitance is changing, then that XL equals to XC is also changing. Okay, that's why if you see 0 volt, 1 volt, 2 volt, 3 volt, 5 volt, these are the reverse bias voltage across the vector diode, and it is changing. The resonant frequency is shifting or a lower or a higher. Okay. So again we got a frequency reconfigurability by simply changing the reverse bias voltage of a vector diode. There is no change in the structure. Okay. Only we are changing the reverse bias voltage. Okay. Similarly, here we are doing the pin diode on and off. Okay. Now this is the combination of these two, where we are using the pin diode as well as the vector diode to switch the band as well as to change the frequency. Now CR technology, cognitive radio. Okay, so here actually it is a modified version of a software defined radio, and it is used for better usage of spectrum. It sets the radio environment and then decide what we have to do. Okay. So it is actually a more advanced one, more intelligent one. CR technique, cognitive. What are the fundamentals? If you are communication person, then it is clear to all of you that what is CR. I have given a small introduction. In case of a CR system, we are actually divide the user into two different parts. One is the primary user, another one is secondary user. In case of a primary user having its own spectrum. It is the owner. He actually purchased that spectrum. While the secondary user has used the spectrum, if the primary user not use that part of the spectrum, then only secondary user use. Okay. So what CR do? CR firstly identify the spectrum modes, that is the ideal part of the spectrum, and allow the secondary user to communicate over that spectrum modes. Okay. Second thing is that now how can we design an antenna for CR? So if you want to design an antenna for cognitive radio, then first you have to design a sensing antenna, that is a wideband antenna. It is used to sense the spectrum, which part of the spectrum is idle or which part is utilized by the primary user. Okay. And second one is a communicating antenna, that is used for the communication purpose. Okay. Now we have two different modes for CR system. One is the interleave, another one is the underleave. There is a small division of these sections. One is, if I am talking about the interleave operation, so if in case of an interleave, if the primary user use that part of the spectrum, it is not used by the secondary user. Okay? Only the primary user use that part of the spectrum. Okay? But if the primary user not use that part of the spectrum, then only the secondary user use. Okay? While in case of underlay, both secondary and primary user use the spectrum simultaneously, but if secondary user actually if the secondary user creates some interference with the primary user, then only the secondary user goes away from the communication part. Okay. So this is the difference of interleave and underleave. Now we have to design an antenna system for such type of system which is used for sensing application. First it sends the spectrum, then if it is working for interleave, then we have to identify which part of the spectrum is not used by the primary user, and then we allow the secondary user to communicate. Okay. So initially this type of antenna is designed first in 2014 by White One. He is a US based researcher, and he actually developed this antenna, but different antenna he used for interleave purpose and underleave purpose. Okay. The same antenna is not used for interleave and underleave. Okay. So this is the problem associated with this antenna. Now, right now, currently, most of the researchers are working on this multifunctional MIMO CR system, which is used for 5G communication system. Here, the same MIMO antenna is used for sensing purpose. It is also used for interleave, and it is also used for underleave. Multifunctionality is there. Okay, it is used for sensing as well as for interleave as well as for underleave. Okay, how can we do that? I have given one example of this 4-port MIMO cognitive radio for sub 6 GHz 5G application. Here, firstly, the author has designed a wideband antenna. And wideband antenna, it is working from 2.5 to 5.5 GHz, and this antenna is used for sensing purpose because it is a wideband antenna. Okay, so it is used for a sensing purpose. After that, the authors have used this CSRR structure in a field line, okay, and make this CSRR reconfigurable. Okay, as it becomes reconfigurable by using the varactor diodes and the pin diodes, the authors have converted this structure into a reconfigurable structure. Now, as this is placed on the feeding part. This structure is placed on the feeding part. Okay. Now, as we change the reverse bias voltage of varactor diode, then this is changing. The resonant frequency is changing. Okay. Similarly, if your pin diode is on and off, then it behaves like a band pass filter, or it behaves like a all pass filter, or it behaves like a band notch filter. So we have developed 3 different characteristics with the help of pin diode in this structure. First is all pass filter, second is band pass, and third one is band notch. Okay. So initially, if you see, when all the pin diodes are on, then it behaves like a wideband structure, and it is used for sensing purpose. After that, when we apply, when one of the diode is on or off, then it behaves like a band pass filter. Sorry, band pass filter. And if I change the reverse bias voltage of varactor diode, this band pass characteristic is changing. Then it behaves like a, it is used for interweave application. Because in case of interweave, first we have to identify which part of the spectrum is idle. Okay. So first you identify with the help of sensing antenna, and then start transmission on that frequency range. Okay. In case of underlay, both primary user and secondary user communicate at the same time until and unless the secondary user not start any interference with the primary user communication. ठीक है, अगर if it starts the interference, then the secondary user goes away from the communication. Okay, so we have to create some band notching. ठीक है, that part creates some interference. ठीक है, उसके लिए हमको क्या करना पड़ेगा? Band notch करना पड़ेगा. तो we have created a reconfigurability in this band notch with the help of varactor diode. Okay, so by doing this, by changing the reverse bias voltage of this varactor diode and by on and off of the pin diode, we can create three different types of characteristics that is known as a band pass, all pass and band notch. And by creating these characteristics, you can design an antenna for CR system. Okay, cognitively, which is a more smart. It is used for efficient utilization of the spectrum. Now come to the millimeter wave. Initially I start my discussion with the DRA for a lower frequency communication system. But I have discussed this thing that as you increase the frequency, the DRA become more efficient in terms of size as well as in terms of gain. So if you see the structure, it is working on a 28 gigahertz, which is not exactly the millimeter wave, it is a lower millimeter wave, you can say that. Okay, in that case, the size of the antenna is very less, 9.5 mm into 7.5 into 2.54 mm. This is the size of the antenna. Okay, and if you see the gain of the antenna is 10 dBi, approximately 10 dBi at such a high frequency. If you are comparing this gain with the microstrip antenna gain at this frequency, then microstrip antenna gain is approximately, or even it is in negative. Okay, it is approximately 0 dBi. Okay, this is the advantage of DRA at millimeter wave frequency range, which is very important for 5G communication system. Okay, so this is all about the millimeter wave. Now come to the part of filtering. Right now we are talking about two important characteristics in 5G in case of an antenna. One is known as filtering antennas. Another one is also known as quasi-isotropic radiation pattern. So what is, in case of filtering, we are creating some radiation nulls inside the structure so that it behaves like the antenna itself behaves like a filter. If you see here, if you see carefully, your operating band is from 1.7 to 2.1 gigahertz. Okay, and in this operating band, the gain is approximately 5 dBi, while outside the band, the gain is drastically reducing and it is going towards the minus 30 dB. Minus 30 dB. Okay. Let us suppose that if the gain is minus 30, what is the gain? What is gain, antenna gain? Anyone? What is antenna gain? What is its significance? Have you heard the term gain previously? As an electronics engineer, you have heard about the gain. What is the gain? What is gain? Gain means you have given some power and some output power is
P out by
P in. So
P out by V.
that means we are usually use the term gain in an active devices. Have you heard the term active device, passive device?
Yes.
So what is the difference between antenna comes under the category of antenna comes under the category of
Passive device.
passive device. It is a passive. Why we are using the antenna gain term? Because gain is usually used for active devices. It is not used for passive.
Open.
Okay.
Yes.
Yes. Open. It is used in BJT, open or FET. We are usually use the term gain. So an antenna is a passive device. Why you are using the term gain here? Gain means here the gain means you are comparing your radiation pattern with some standard antenna. Let us suppose that it is an isotropic antenna. You are comparing the radiation intensity of your antenna with respect to some standard antenna. Like we have an isotropic, that's why the antenna जो gain units are dBi. dBi means with respect to isotropic. dBd is also a unit of gain. That means you are comparing your antenna gain with respect to your dipole. Okay. Similarly, the antenna gain having a unit of dBIC also. So dBIC means you are comparing your antenna gain with some isotropic circular dipole antenna. Okay. So the gain term in antenna is a passive device, but we are using the term gain because you are comparing your antenna's radiation intensity with respect to some standard antenna. So come to the topic again. Here the gain is minus 30 dB. That means it is not receiving any power at that frequency and behaves like a filter. Because in this area where we have an operating band, then the gain is 5 dBi, and just after that band we have a minus 30 dBi. Okay, no receiving outside the band. Okay, so it behaves like a band pass filter. Okay, so this type of antennas are widely used in 5G communication because it reduces actually. When you see the front end of the communication system, then we have an antenna. After that antenna, we have a band pass filter to reject the outside band frequencies. Okay, so this type of antenna terminates this requirement. Okay, terminates this requirement that this antenna itself behaves like a band pass filter. Okay, that's why it is called as a filtering antenna. Okay. So it is widely used in 5G communication. Now come to the another topic, and the topic is quasi-isotropic radiation pattern. I think all of you are aware with the isotropic radiation pattern. What is that isotropic radiation pattern? It is radiated equally in all the directions. Okay, and it is a hypothetical concept. It will not come. It is used only for mathematical modeling. Okay. Now, designers have developed a radiation characteristics which is quasi-isotropic. Quasi-isotropic means it is omnidirectional in both the principal plane, E plane and H plane. Okay. If your radiation pattern is omnidirectional in E plane as well as H plane, that type of antenna is called as quasi-isotropic. Okay, and it will be developed. It is developed through if your antenna behaves like an electromagnetic dipole. Electric dipole, I think all of you are aware with the electric dipole and the magnetic dipole. Electric dipole having a radiation pattern, eight-shape radiation pattern in E plane and omnidirectional radiation pattern in H plane. Similarly, in magnetic dipole, we have an omnidirectional radiation pattern in E plane and eight-shape radiation pattern in H plane, just reverse. If your radiator behaves like electric magnetic dipole, that means at the same frequency it behaves like electric dipole and magnetic dipole, then you got a radiation pattern omnidirectional in both the planes, E plane and H plane. and that is called as quasi isotope radiation pattern. So it is also used. It is actually a you can say that it is a it can be used in place of a circularly polarized antenna. Okay. Thank you so much.
Now, in the conclusion, we extend our heartfelt gratitude to Dr. Anand Sharma sir for his invaluable contribution as the session chair. Your depth of knowledge, dedication and insightful guidance have enriched this session. As a token of respect and appreciation, we are honored to present this certificate acknowledging your significant role in fostering academic excellence. Thank you, Dr. Sharma, for your unwavering commitment to education and research.
मैंने बोल दिया